thanks for your invite. You mentioned Lausanne, and so it's good I have this first slide because it's always nice to show where I am. Actually, we have some satellite campuses, and so I'm not in Lausanne. I'm in Sion, and so we have like a small campus here in the mountains. So I'm now here on the fourth floor, can see our castle and the mountains here. And so in this campus here, we focus like on energy-related applications, mostly in chemistry. And as was mentioned, I focus on using the data perspective on those things. And so before I forget to thank all of the people involved in this, I want to start with the thanks because it often gets lost in the end. So of course, many of those things, especially with the Cheminfo ELN, goes to what Luke Partini has started. I'm in the Baron Smith group, and some of the works I will show are in collaboration with some of the companies shown here, but also with the AIDA Materials Cloud teams, also at EPFL. And so what I'm going to try to do is to basically start with some ML applications and then use this to motivate to the capturing of data in some reasonable form. Because this was also the way I started my PhD thesis. So in Baron's group, we have both simulations and experiments. And so my hope was to basically bridge those two using ML. But then, as I think all of you know, and getting the data is not that easy. And so this turned out to be also a focus of the work I've done so far, mostly with Luke. And so what we're going to do is we will go through different scales, starting at the atom scale, see how we can use ML there, go to the mesoscale with some polymers, and then usually I end up in the industry, but I will drop this to focus a bit more on the ELN part. And on our way, we'll see how we can use ML to capture insights from the data to learn some new chemistry, to guide our search through design spaces, but then also in the end to help us also in curating data. And so our journey will start at the atom scale as promised, and with something that's really really at the heart of chemistry, which are oxidation states. And so, I mean, this is something we chemists often think about because reactivity deals with this, and we reason about our reactions in terms of oxidation states. However, it's interesting to note that they are not quantum mechanical observables. So there's no operator in quantum mechanics that allows you to measure those oxidation states. So they're in the end, as bonds, just convenient fictions. And so for organic molecules, you might be able to count just bonds and then use some valence-based counting. But for more complex materials, it's quite likely fails because then it's even tricky to find what a bond is. And so what you use for crystals often is something known as the bond valence sum technique. And this is something where you basically have kind of an exponential. And in there, you will have an R0 and your bond length and some universal factor B. and then if you sum up those bond valence terms, you're supposed to get the oxidation state. And if you try this in practice, at least we found this didn't work so well because you don't have all the parameters for all the element pairs. And then, of course, you need to define what bonds are and those kind of things. But the interesting fact there is, of course, that chemists are quite good in doing this. So if you asked some chemist and just showed him or her a compound, they usually just know by looking at the compound what the oxidation state is. And so could we basically just mimic this using the data we have from chemists and building also voting machines for those oxidation states? And so to do this, we have to somehow then tell our model what the compounds are. And so in our case, we of course have to focus on the chemistry of the element we want to focus on, like where it is in the periodic table, what it's surrounded by, the local chemistry, and then also the shape. And probably the interesting part here about the shape is that we don't have any kind of counting of bonds or whatever. We just measure similarity to our ideal coordination quality for like similarity to our ideal octahedron, tetrahedron, whatnot. And then we have a feature vector that basically tells us what the chemistry surrounding our center is, as well as what the geometry is in terms of how similar it is to the ideal octahedron, tetrahedron, whatnot. So we have a bunch of those similarity measures. And then what we can do is we can start mining data. And so we can go to the CSD, and if you look there in the chemical names, since the oxidation data are at the heart of chemistry, you have those numbers there. And so the interesting fact is that they come from different sources. So some chemists might use intuition to assign them, and some might use XPS and as other way to measure them. Some might do something else. But in the end, you always have the editor, who is a chemist at a CSD, that also thinks that this is reasonable. And so we have this wide variety of oxidation state assignments that come from different sources. And we have our way to convert the structures into numbers. And then we just mimic our ensemble of chemists who all use different ways of assigning those oxidation states with a bunch of different models. So we have an ensemble of models, all have their own way of reasoning, and they will all give their own vote. If it's easy, they will all vote the same. If it's more tricky, they will have different votes, and then you also have a measure of the uncertainty of your model. And then you of course can see it works, and it's of course not surprising for some of the parts of the PSE. But the interesting part, you can also improve by removing the uncertain votes. So if you remove the uncertain predictions, what you see here below, you see that the predictions improve. So what you see here, if you didn't see those plots before, is that you have the actual oxidation states on one axis, the predictions on the other one, and you would like to have blue 100% on the diagonal, and everything on the off diagonal is something by the model confused something. But the perhaps more interesting thing for the data management part is that we can now also use models to find mistakes in the CSD. Because I told you that we have this uncertainty estimate, so we know if our models agree or disagree. And then we can just look for cases where our model is really sure, but it doesn't agree with the CSD. And then what we do is we go through a bunch of those cases and then fill table after table after table in the SI, and where we just list all the typos we find with this approach. And so you really see what the power of some ML or other approaches could be in ELN. And you could have those tools there to just give a warning to a chemist if something seems messed up in their data entry. And so I mean, this is what we also now try to do for other things, not only oxidation states. And this also works for some of the tricky cases. Like if you have, in the case of MOF, you might activate them to remove the solvent. Sometimes you have a small change in the coordination. And in this case, you basically see that you elongate of the heat run, and we also capture those small changes. And so we use this now routinely for our DFT simulation, because what you need to do there is you need to first guess the oxidation state to initialize your system. And this is not used in our case in practice. And it sometimes also helps to at least get some ideas what all similar compounds are, because in the end, you can also always look at what's the most similar coordination environment and see what the oxidation states there were, and then get inspired by this. And so this was really just to show you that it can also have a value in like highlighting potential mistakes, and what also help you get inspired by similar chemistry that you might find somewhere. So now we have a model, and then the question is, what can we do with ML models for material science or also chemistry? So I'm officially in, I think, the engineering department at EPFL, the chemical engineering department. And so we care about making good materials for some application. And this might sound easy in the beginning. However, you usually have more than one objective you want to optimize for. So even if you have a reaction, you might want to optimize for reactivity and selectivity. If you have a material, you want to optimize for hardness and ductility. And often those things are also competing. And a priori, it's often not clear like what the best balance between different goals are, like what is more important for your application. And especially if you do this like in silico, like in a computational screening, you even know less about what is important and in terms of trade-offs between different objectives. So the best you can often do is you can just like look at the objective space. You have objective 1 and objective 2, and then you have some materials in there. Some might also be catalysts or some other compounds, And the best you can do is find, in case you want to maximize both of them, this red thing here, which is known as the Pareto frontier. And you can see as mathematically that if you just mix those two objectives in some way, you often you won't find all the solutions. So if you just start a screening, the best thing you can do if you don't know what is the most important objective is to find all the ones that are here on this red line. And so how do you find those red materials? Of course, chemical space is quite immense. And so just going brute force through this design space doesn't work. We don't have enough time to do so. However, also building some kind of ML model might fail because you have many more points that are down here that are quite crappy, and you have only a few points that are up here. And so how do you efficiently find the important red points without losing too much time? And this is the question we're going to try to answer here. So how do you find with confidence that you don't miss too many of those red points, this Pareto frontier in your design space? And so we did this together with BASF when I was in New York with them. And so what they do is they have a business for surfactant, which are some kind of polymers you have in solution to enhance the color strength of pigments. And they have different things that their customers want from those surfactants. So you want them to be adhesive, you have some color brightness, and you want them to be not too viscous. And then comes the challenge that you have like this huge design space. So they constrain it already. They have some building blocks they consider. And of course, you could now try to ask some chemists to make them, but like with 53 million polymers, I mean, no one will try to make this for you. So there's no way to test all of them. And so the next thing you might then come up with is, okay, Kevin, you come from Baron Smith's group. You probably can do some simulations. And so, of course, we can approximate those objectives of simulations. We can get absorption energies, repulsion energies, and some measure of how long and crowded those polymers are in solution. However, like those are complex simulations, and one of them for one polymer might take a week or so. And so even BASF didn't want to pay for this. So you have to be more clever than this. So experiments don't work, and simulations don't work. And so the fancy new thing everyone is doing is machine learning. But how do you now replace your simulations with a model? So how do you train your model? On what data do you train your model? So of course, you'll have a perfect model if you train your model on all the data. But then you didn't win any time. I mean, you just trained on all the data, so you had to compute before everything. So this doesn't work. So the best way would be if the model somehow could tell you what it wants to see. So if you would have a feedback from the model to you, what it wants to see, to be trained on, where it learns the most from. And so to do this, you somehow need to have this feedback loop from the model to this thing doing experiments or simulations to tell it what to do next. And for this, you need to have two ingredients. So the usual models in ML will return some kind of mean, what is just your prediction. But you also need to somehow balance how uncertain you are, because you not only want to optimize to go to like the Pareto frontier, but you also want to be sure that you're right there. So we will have models that return both a mean and also an uncertainty. And once you have those two ingredients, you can start doing something quite interesting, which is quite simple in the end, but it helps quite enormously. So what you can do if you have those things, you can go back to your objective space. So you have objective 1 and 2, which might be activity and selectivity. You get your predictions from your model, which are now just the means, so just the points. And in the beginning, they would be quite crappy. So if you start with only a model in the first round, it will be quite bad. The model is still quite unsure. But you can now just add the uncertainties to this picture. So you can just draw now those rectangles there. And those rectangles are nothing else than just the uncertainty in objective 2 here, and uncertainty in objective 1. And we will also end up scaling them, but this doesn't matter. But you just basically have the error bars as the edges of your rectangle. And if you go to 2D, you have rectangles. If you go to 3D, you will have cubes. And if you go to higher D, it's hard to imagine, but it's like a hyperrectangle. So you have those hyperrectangles, and now you can start looking at them. And looking at them is quite interesting because what you will see is that some of them are below the others. And so if you have good uncertainties, which you can get guarantees from the theory, you know for sure that all those red ones here are bad, because here the optimistic estimate, like the top one here, the best case for those is below the worst case of all the others. So even with the first scrappy initial model, you can throw away most of the design space. So you can always start throwing away all of those red points because they are of no interest for you. And you know for sure that those here, where the worst case, the lower bound here, is above the best case of the other ones, that they are the good ones. And the next best thing to do is then, of course, to focus where you're still a bit uncertain and unsure. So this is like here. And so the next thing to do would be that you sample in this part of the design space, you retrain your model, and then at some point your model will be confident, and you can then classify all the points in this design space. So how does this work in practice? This is this plot you see here. So the y-axis just shows some kind of error measure in like a multi-objective space. So we measure basically the area you cover with the Pareto frontier. And then you have here on log scale how long your search takes to basically find all the good materials in this design space. And if you have no clue, you can just do a random search, and then you will get a learning like this. And of course, you will have some kind of error band here because you can start at different places to random search. And so you have some kind of uncertainty. But this is how the naive approach without any help from ML would look like. And now we can add our ML, and you can, of course, tune this. And there is some theory behind how you can tune this. But you can then get massive speedups. So I mean, this is log scale here. So with only 4% of what you did before, and you can recover the same error. And so unfortunately, I cannot tell you what we found there because this is IP of BASF. But I can tell you that they're looking now into the polymers we found there, and it's also used in practice there and in other groups. But the perhaps more interesting thing is that you can also apply this in some other common setting. So let's say if you are in a lab and you have 3 objectives, and 2 of them are quite cheap and 1 of them is expensive. So you have objective 1, 2, which might be something you measure like just routinely, I don't know, NMR, mass spec, you can get this within hours or days. And then you have a third one, which is really a mess to get. It takes you months or weeks. You may have to go to some light source to get this third objective. So somehow you would like to measure for all your materials the first 2, but you would like to avoid measuring the third one because it's really expensive to measure this one. But you would still like to get some speed up with ML in this case. And if you use some special model that also models how those relationships are between the objectives, because usually just model the relationship between the features of your polymers and the outputs. But if you also model the things between the outputs, you can also apply this, this approach here. And then basically those measurements will fill in for this that you skipped. And you can also get speedups that are a bit less, but still also with missing data in this approach. And so this is used now also in other groups like in Liverpool, who really want to find the best materials in some design space with some tunable certainty, because you can derive for certain models that depending on how you scale those rectangles, you will be with some certainty recover the important solutions in this design space. And so, of course, we are now at the NFDI for chemistry meetup, so we have to also talk about software. All of this is like in this open source package, and you can use this with various models, with ensemble models, with Gaussian processes, and also use this in batch mode if you want to like sample directly 10 experiments at one time. But I mean, this was just like a short excursion to show you how ML can also help you to optimize things and to recover important solutions. If you would like to also find a model that is optimal for finding conditions for a reaction where you want to optimize like yield and other things, you could also use the same approach there. But now coming to the final part is how do we get the data into our models? And this is something where, I mean, I hope my PhD would focus a bit more on, but it took a lot of time. And I mean, you all know it's quite hard to get this right and to get started and to get people using those tools. But I mean, those are the questions you want to answer now, like how can you get the data into a form that you can use them for those ML approaches? How can you help people collaborate across the globe? Because in the end, science doesn't just happen in a Euro group, but it will also happen in large collaborations, perhaps across the globe. And so in our case, I mean, Bern still has close links to Berkeley, and so you might also want to collaborate with people there. And then also, I mean, we have all of those fancy tools, and I mean, they might seem interesting, but in the end, if no one uses all of those tools that we develop, they are of no use. So how do we bring those tools I just discussed in the first 2 parts to the chemists? Because I mean, we might have some nice theory behind them and we really like them and have nice plots, but if they're not useful for them and not usable for the actual bench chemists, they are of no use. So how do we bring all of those fancy tools also to the bench chemists? And so to get this started, it's perhaps nice to think about what at least I might do this weekend. And so when I wake up, maybe I want to have some pancakes. And so if I want to have pancakes and I have no clue how to do them, I might just go on Google and Google for pancake recipes. And what you will find there is that Google can compile your recipes on different sites into a nice table. So you get the ratings, you get the ingredients, you get the time it takes for different recipes on different websites. And in the end, I mean, in chemistry, we also often deal with recipes. I mean, method sections are also some kind of fancy recipes, which we write in PDFs with a lot of acronyms. But in the end, we also deal with some kind of recipes. However, we are quite far away from having something like this for chemistry. And this is possible for like all the other parts of our daily lives, like recipes for cooking, because those websites embed their data in some structured form in the website itself. So in this case, they use some markup from schema.org, and then search engines like Google just know what to look for and what those things mean. So if you have recipe on some recipe site, you will use this markup, and then search engines can look for those things and then compile it in a reasonable way for you as the end user. However, we as chemists, we somehow are still stuck in some PDFs, and we like to report data just in weird old-fashioned forms in PDFs. At least this is my impression I got. And so when I was still in my undergrad, we often had to write the color of like of our compounds or of some change in the reaction in our reports. And I struggled to name the colors. I mean, was it now blue, blue-violet, or something else? And if you look into papers, this is how we report the colors. We just put some name for colors in the papers. And also in the CSD, you have the color as text string in there. Then when I got into this data management, I just wondered if this, in the past, where I had to ask my friends all the time, is this now blue-violet, is this pink, is this blue? And if it's just me or also happens to other people. And so what we did is we just took the colors of all the MOFs you find in the CSD, like the call names of all the MOFs, and then just asked more than 5,000 students, professors, and staff at EPFL to just tell us what color they see when they read this color name. So someone might tell in the CSD that their compound is red-brown, deep yellow, or beige. And then we just ask other people to pick what they associate with this color. And you see the responses here. So you might report in your paper that your compound is beige. and you actually mean like this color, but for someone else, it's this here. And so, of course, this is somehow a bit messed up because this, of course, limits reproducibility and also hinders reuse of the data later on. So the initial idea was to build a model that can predict those things, but because those colors were reported in this messy form as names, it was really hard to build a model for those kind of things. And so how can you fix this? In our case, we fixed this by building a better pipeline for capturing colors for compounds. So you can get quite cheaply a color calibration card. You have always your smartphone with you. And so you just put this card next to your compound, you take a photo. Then we have a chatbot. You can just say your sample name and your username, upload your photo to us in this chat. Then you will have the photo in your database. We, of course, can calibrate the color of this photo because we have the reference colors in this card. And you can now report your color as a number, like not only as like some random string. But if you want, we can also give you the string discloses in the XKCD table of colors. And so you can also put both the color number as well as the name in your paper or wherever you want to report this color. But the interesting part then is, of course, once you have all of this in the ELN, and in the Cheminfo ELN, we have one button that allows to export a bunch of entries onto Zenodo. And what we will have there is that you will have a table of contents, which is a JSON file that lists all the entries. And for each sample, there will also be another JSON that lists the attachment files as well as some basic characteristics of this thing. Of course, you have the DOI from your entry of on Zenodo, and you will also in there have a link to some website which can then open those files on Zenodo and make them explorable. So if someone follows this DOI in your paper, they will end up on Zenodo. And then there's another link they can click if they want to then explore all the measurements you report in this entry. But a quite common thing that's still missing in this picture is that even if you have all of those fancy measurements, in many cases, just measurement alone isn't enough. So in my field, in the field of metabolic frameworks, we often measure isotherms. And so what you do there is that you have some kind of measurement where you increase pressure and you measure how much gas you can load in your compound. So your compound might be a MOF, a zeolite, whatever has pores. And then you just see like how much thing you can load into your compound as a function of pressure. And I mean, this might tell you different things about your compound, but it's even more interesting if you know what a reference is, because how much you can put into your compound depends on how empty your pores are and if you have defects in your compound. So if you have defects, you might be able to put more into your compound than if you have a perfect crystal. Vice versa, if you have still solvent in there, you'll be able to put less into your compound, into your less gas into your crystal. So you would like to have somehow your reference isotherm of your perfect crystal. And so how do you get this reference isotherm? And so, of course, you can always just ask your friends upstairs in the simulation group to get one for you. But somehow this is annoying. You always have to go upstairs and ask your friends there to get you just this routine isotherm, because for them up in the simulation group, it's just routine and it's boring to do. But of course, it's hard if you're a bench chemist, you want to install some codes and run simulations, even though you need this data to really extract all the insights you have in this isotherm. So what we do is we just make this routine simulation routine again by adding a button in the ELN to get this for you. So if you now have a CIF file that you get from, let's say, XRD in your ELN, you can request with one button different simulations in our ELN. And in our case, we collaborate with the Materials Cloud team and with the IRA team who have the IRLab simulation platform. So we have both REST APIs, and so we can basically submit the structure to IRLab. run simulations there and get results back in the ELN and compare then those measurements. And so, of course, there's still a gap between what you can run into the simulations, because if you just get your CIF file after, let's say, a read file refinement, you might still have disorder, you might still have missing hydrogens. And so there's still something you have to do before you can run a simulation. But we try to help you in this process by having some checks there. So if you click this button in the ELN, you will end up at this page here. And this will run some checks for you that looks if the structure makes sense for simulations. And it also tries to fix it if it doesn't make sense. And then after that, you can select also the protocol that you want to run. If you just want to run a quick task or like a test or a really well-converged simulation. This will have a DFT workflow under the hood in an EDA that is basically with error fallbacks. And it will just run this for you without any coding. And then it will also run the next simulation also for you. So in this case, you might ask for an isotherm. You need to get the DFT optimal structure, then some partial charges, and then the force field simulation. And it will run all of this for you after just clicking this one button here. And then you get the result back via the REST API in the Cheminfo ELN. You can start comparing those two plots. So you can compare your simulation with the actual isotherm, and then hopefully they are similar, but often they are not. And this overlaying of different spectra or measurements works that easily in the Cheminfo ELN, because the Cheminfo ELN, and this goes back to what Luke started, has, I think, a different philosophy from many other ELNs. So for many other ELNs, especially commercial ones, the ELN is somehow just a place to take notes and maybe attach some files to this. But we think that the most important task an ELN can do for you is to make the data fair, to really take the hassle of converting the data into a fair machine actionable form. And so this will mean that the ELN also has to do this boring task of parsing the files. Because otherwise you just put in some kind of closed source file. You might still have the license for this while you're still at university, but then you leave at some point, you lose the license, and then you're stuck with this somehow closed, messed up file. But once you convert everything into some kind of open format, in our case, it's really JCamp, you can use the same tools for all the spectra. And you, of course, also, after you leave, you just have a simple text file that you can just export. And then in our case, how we deploy this thing is that most groups also have a nightly dump of all the data onto some other server as just a zip file. And so they just have like the full file structure with all the reactions and attachments on some server where they can just open the folders for all the students and have all the spectra in there. And so they don't really need to worry that they cannot leave this ELN at some point. It's really important for us that you can at any point easily jump out of Cheminfo if you don't like it anymore, and if you want to put a different ELN. Whereas if you go with many other also commercial ELNs, you're often just stuck with them, and it's really hard to get the data out of those ELNs. And so this is in the end also quite tricky for reactions. I mean, this view doesn't look as fancy as the Chemotion view. It looks a bit more old-fashioned, but I think we have a quite interesting concept. At least the user like it for capturing reaction metadata. Because reactions are that flexible, I mean, you can have many different ways of running them, and you could have like a really huge form with a lot of different fields to capture all potential scenarios of temperature, RAMs, heating, rates of heatingness, whatever you do in your lab. So even if you go to material science, here they have like 10 different ways of heating the reactions. And so having a form where you just have to like fill dropdowns or checkboxes with those things will become unusable at the end. And so what we try to do here is we try to basically keep the interface relatively close to what the chemists are used to from the pair-based lab notebook. where you might have like a short table and then some text. And in the text, you describe what you do. And so in our case, the way you describe the stuff is via some shortcuts. So in your group, you can define a bunch of shortcuts of operations that you do quite regularly. So in our case, our moth chemists like to heat their moths in a microwave or some other oven. And they have like a bunch of shortcuts of different ways of heating their reactions. And all of those shortcuts, they have some special fields in them. And those fields are parameters that are in the end searchable and also standardized in the ELN backend. And so what you can do is you can, if you in the microwave, you can just start typing M and then tab complete, and it will then fill in a sentence for you with some empty fields, which might be a temperature and a temperature ramp. And if you fill those, you will extract those directly on the fly and attach them to some schema, and it's searchable in the database. And so in this way, we try to bridge both that having the text in there, but also having the important parts in some kind of table that's searchable in the end. So you do insert those tags with tab completion, and we will have those fields you can fill in. And if you fill those in, those things will be in the main searchable part of the ELN. So if you look for certain kinds of temperatures, you can search those temperatures from the main search interface of the Cheminfo ELN. So you could then basically look for T ramp in a certain range, and you have then all reactions that have this certain type of temperature ramp, because those things end up in the main index. And all of this is possible because, I mean, all of this is written in JavaScript. And Luke, it's some long time ago, before my times, started to basically develop all of those basic things for just doing stuff for science in JavaScript. And that there was not that much out there, also just do basic stuff with arrays. And so the things he started developing there are now also used widely beyond chemistry. And so this, I mean, also shows that if you develop your ELN based on really small modules that are reusable, they can also use beyond your own small domain, which might be chemistry. And they can also allow you to be a bit flexible in developing new tools. And so one way we use those tools is to try to give chemists some carrots. And so in our case, those carrots are hopefully tools that make the life of chemists easier. So you saw a lot of ML packages there. This is something I'm also trying to bring into the ELN. So what we already have in there is that we have this PCA view. What you can do there is you can just load a bunch of spectra from different samples in there in the ELN. And then once you have loaded them, you can apply some unsupervised learning on those different spectra. So in this case, you have this PCA view. You can apply different filters like baseline correction, centering of the data to all your spectra. Let's say if you go to synchrotron, you have like in situ measurement XRD of some sample, and you want to see like when you have certain groups of spectra across like all your 1,000 spectra. And so if you now can do this with PCA, you can see like your different clusters and can just explore like which spectrum belongs to which cluster and like what part of the spectrum is important for making those clusters up. And you can, of course, apply all of the filters in a consistent way to all these spectra. And we're now doing the same also for supervised ML. It is if you have some features or like some compounds and some targets. We are building now the pipelines to also build models for this directly in the browser to allow you to also to build at least simple models and get some feeling for how this works and if there's something to learn from your data. Another carrot that comes perhaps from my lab is, in our case, the people often measure XRD patterns. So of course you can just import your, let's say, BRML file from Bruker in there. You can apply always the same tools to all aspects like peak picking and auto peak picking. But we sometimes also have additional tools. So in this case, we also have this prediction tool. So you can just select a CIF file that you might have in the ELN. And then once you did this, you will also get a prediction for the XRD into your ELN. And then the nice thing is that you can also then change the parameters of the cell. Like if you want to model like a solvent effect by having a larger A parameter for your cell, you can also model directly in the ELN in the browser. And you can also, if you know what compound you want to make in the COD or the CSD, there's also a search field to basically look directly for your compound and get the patterns for those compounds also in this view. A recent addition is that I had some interns helping me to also bring DOE, some of experiments into the ELN. So this is important if you do like a screening, like the second part of my talk, if I want to optimize certain things. That's really important that you have a good grid of experiments to do, because often you would just naively do like one factor at a time, that you change like first the temperature, then you change like this amount of solvent, then you change some other things. This is quite inefficient to do this in this way. And there are some ways to have optimal designs for those experiments that are space filling and uncorrelated. And so we packaged them up in JavaScript, and we are now building also the front ends to allow it to use them in the and then with the hope to also use those active learning things directly in the browser. So you really see we try to bring a lot of fancy carrots to the chemists and try to find different ways in which they can also use the tools and we like to develop, but that also help to make their lives easier in certain ways. And one thing that's perhaps a bit closer to my heart is like a recent thing we did with Luke, where we had this tool for IR spectra. And so, I mean, we often teach IR spectroscopy in like the first year in the bachelor's already, because it's like, again, really important for chemical analysis. And so what we have here is with the tools of the ELN, you can just draw any compound and then on the fly get some predictions for your IR spectra. You can have the link between the structure and the animation of the modes and the spectrum directly in there. And so you can then also directly show students, like if you click on this carbonyl, like what part of the molecule moves. But you can also use to explain different effects you have in organic chemistry, like directing groups, mesomeric effects, because you have like those probe frequencies, like a carbonyl, and you can see like how if you add like a halogen, it shifts those frequencies. And so the nice thing is, of course, students can now just like also draw their own compounds. They can just modify those things and then on the fly get the predictions for what they want to see. And if you want, you can also get an intuition for your own compounds if you want have a research question. I mean, we can have a higher level simulation with DFT via the EDA lab, but this is really like within seconds on the fly to get like just a quick intuition for those concepts in the browser. And so what I hoped to give you now, I gave you now is like a really broad perspective on many different things. I guess also a broad tour starting at the atom scale, going then over the polymers, and I hope you trust me that we also can do something for the industrial scale. So there we impressed engineers at RWE that we could find something that they didn't know about their power plant. And then we can use our toolings to guide our search through chemical spaces. And we have like all of this tooling available to hopefully make data a bit more useful and to also bring the tools we developed up to the chemists that hopefully then use them, and that makes their life easier.